Welcome, everyone, and thanks for joining today's session on LLM Observability. I'm Grant Swanson, and I'll be your host for this event. We've got a great lineup for you. Joining me are Kevin Leong, our VP of Product Marketing, and Austin Zhang, who is an AI engineer. They'll walk you through a quick presentation and a live demo. Let's get started. Kevin, over to you.
Thanks, Grant. Um, Good day to all of you who are joining us, and welcome. Topic today is LLM observability. I thought I'd start off for those of you who are not familiar, less familiar with Observe. We are a modern observability platform engineered for scale. We've built it from the start for performance to enable faster troubleshooting and to be cost efficient at large scale. So, what are some of the things we've built to help us do this? I'll walk you through some of these. So, to get telemetry into Observe, we have a real-time ingest pipeline that can handle petabyte per day ingest. This lands data into a data lake, which is the most cost-effective way to store telemetry at scale. And if you look further up, to provide context to the data, Observe maintains a knowledge graph that structures the telemetry for fast search and correlation. And that's actually a big reason for how Observe can deliver performance at scale. So move further up for troubleshooting and investigation. Observe has multiple explorers that allow users to analyze their telemetry that's in Observe, whether it's log analytics, infra monitoring, or APM. For our talk today, we're primarily going to be talking about the LLM Explorer portion of this. And then above that, a newer way to analyze data and observe is through all the AI SRE, which allows engineering teams to use natural language and chat-based interactions. And the goal here is to help users resolve complex incidents faster. So in a nutshell, that's what we mean when we say Observe is engineered for scale. And we have customers like Capital One, Topgolf, Dalpad, who typically choose to go with Observe because they're able to get the performance they need, because they can resolve incidents faster, and also because of the ability to store, lots of data, hundreds of terabytes or petabytes of telemetry at much lower cost. Now, for today's topic, we are focused on LLM observability. And here's why this is a topic that has gained importance over the last year or couple of years. And what motivated building LLM observability into the Observe platform were the proliferation of usage we've been seeing in the market. Use cases such as customer support, virtual assistants, content creation, language translation, code generation, etc. That's very common in the market today. Aside from that, there's also a move towards embedding more Gen AI functionality into applications. These figures come from a Gartner study where they're predicting that the percentage of ISVs, that's independent software vendors, the percentage of ISVs embedding Gen AI into their products will grow from 5%, that's back in 2024, to in excess of 80% in 2026. So that's a big leap and perhaps not surprising given the disruptive nature of AI and how many software providers are researching ways in which they can harness the benefits of AI in their product offerings. So that's one significant market trend as well. And then the metric on the right comes from a usage perspective for these LLMs. Gartner also estimates that 30+% of the increase in demand for APIs by the year 2026 will come from AI tools and tools using LLMs. So that suggests to us that LLMs are going to be driving significant demand here. And with an increase in demand and consumption, there's no doubt a need for observability in the LLM space and for that to mature. So that's another indicator from the market that has bearing on why LLM observability is needed today. So with that, let's talk more about how Observe is helping our users on their development of LLM-powered apps. Here is a high-level representation for where LLM observability fits with Observe. So going beyond standard observability for monitoring applications, we also instrument your AI apps such that Observe can collect telemetry, when it sends prompts and receives responses from LLMs. LLM observability allows us to track things like the input to, the output from the LLM, which tools were used in the process, and in terms of usage, things like tokens used, duration of LLM operations, and any errors that may occur. So this is what we're going to be diving into today. And it's my pleasure to introduce Austin, an AI engineer here at Observe, who can walk us through how we can set up our app to benefit from LLM observability and also some common workflows for how we can use this telemetry. Austin?
All right, thanks, Kevin. Can you all see my screen? All right. So thank you for the introduction, Kevin. In order to understand what LLM observability is, I'm going to first walk you guys through an example use case that we've been developing here at Observe called the Ollie AI SRE. I think Kevin touched on this briefly previously. So the AI app that we're going to use for this demonstration is a natural language interface by which an engineer or an SRE could ask questions of Observe in natural language. And our agentic workflow will then go into Observe, look at Kubernetes and Service Explorer, and pull in data from all of the things that we've ingested from the customer in order to show a visualization that answers their question. As for how this is set up a little bit more in detail, it's a multi-agent framework in which there's an orchestration agent here and an observe agent here. This is where the actual LLM calls are happening. So a natural language instruction would be passed in. A high-level orchestration agent would then send a call over to OpenAI or Meta or whatever large language model provider to ask it, hey, given that I have these tools in this sub-agent, which one should I call in order to actually answer the user's question? And if control is passed over to the observe agent, then this observe agent will also go talk to OpenAI or Anthropic or whatever LLM provider with a different prompt and additional context that we've gleaned from the user system and figure out what visualization from Observe should we show the user in order to answer their question. And as part of this, we also do a retrieval step, so RAG, in which we have a knowledge graph that stores different resource values. So for example, what Kubernetes clusters or pods or nodes that you have in your system, as well as the different types of visualizations that we can show you. And we retrieve those in response to the user's instruction in order to fill in the observe agent. And the observe agent is then in charge of taking that context and picking the right OPAL query or visualization from Observe to answer the user's question. For example, we have specific visualizations for CPU usage or service errors or ISE logs, etc. And it will then fill in different parameters for those. So it needs to know, for example, what cluster does it need to find the memory for and what Kubernetes container. And in order to fill this in, we do this resource retrieval, and this is we retrieve values from a vector database in order to find the values that match the most semantically. So for example, if a user asked a question like memory usage for prod, we should be able to make the association that prod is semantically similar to our kubernetes.observeinc.com cluster. And so you should be able to pull that in. This is automatically updated hourly. And so this, of course, is an implementation that has a lot of different moving pieces. And in order to kind of figure out what's going on, like how are these different agents and LLMs communicating? Is it getting the right context that it needs? we need LLM observability in order to understand what's happening. As for how we actually set things up, it was pretty simple. We actually created the entire application and then added observability post hoc using a tool called OpenLLMetry. This is being adopted in, I believe, being adopted into the OTel standard, but this is essentially an open source project that is integrated with all the most popular LLM providers, OpenAI, Anthropic, Hugging Face, Mistral, etc. It only took about 2 lines of code in order to hook this in, and it hooked into all the SDKs that you would use for all of these applications. Supports most of those popular model providers. They have integrations with Python and TypeScript, and I believe several other languages as well. So now that we have kind of an introduction to the actual AI app that we want to observe, I'll go ahead and go into a demo of of how you might want to use LLM observability within Observe. So let's head over to Observe, and the LLM Explorer, which is what you would use for LLM observability in Observe, is under this LLMs tab. And let's go ahead and look in the past 60 days. So the first use case that I want to show is how can we use the LLM Explorer to analyze kind of token usage over time and figure out if there's a token spike, what are the calls, what are the usage patterns that are causing that spike, and are they anomalous or something we need to fix? So if we look in the past 2 months, we can see that we do indeed have a token usage spike here on this overview dashboard. This page shows a broad overview of your LLM app infrastructure. Sure. So you can see like general activity in terms of like how many LLM spans, how many like calls related to the LLM that we've observed from your system, what percentage of them have an error associated with them, what percentage of them are like, chat completions that you've asked OpenAI or Anthropic to give you, or requests for embeddings, or even higher level at the level of like entire agentic workflows or individual tasks inside those workflows. You can also see how much time that things seem to take overall, as well as the ones for individual operations. Up here, you can also filter down to, for example, specific service versions or environments, or even model providers. Zooming in on this token usage chart here, we can see that there is a big token spike at this time. So all I have to do here is just zoom in. And I would like to, and we can see that the time range updated to that part that I zoomed in on. And I'd like to go see, kind of drill down further into what are the individual traces and spans and calls to the application that resulted in this token spike. So for that, we can go into this traces tab. And let's zoom in a little bit further on this spike here. Okay, so it seems like we have a couple embedding calls in which, yeah, it seems like this is the cause of our high token usage. We've been making a couple embedding calls to OpenAI that take up like tens of thousands of tokens each time. And so let's just go ahead and open up the biggest one of these. and drill down further to see what's going on. Looks like I need to log in. Okay, there we go. So we can see for this individual call to OpenAI, all of the features related to it. In particular, we can see like what did we actually pass in? It looks like we passed in 2,048 different prompts. So here we have like a large number of like observed customer emails. These are mostly test emails for the purposes of this webinar, but we passed in like a large embedding batch, and this seems to be the cause of the token usage spike. And on this page, you can see different features like how long did the request to OpenAI take? What model did you use? What are the actual prompts that you passed in? You can even ask things like how many tokens, how many tokens were cached, and things like that. And so by using this tool, we've identified that the cause of this large token spike was a large batch of embeddings that we asked OpenAI to create for us while we were embedding our customers. This does fall under normal usage for us, but we can then check whether or not this large spike is taxing our infrastructure or not. So we can actually pivot from directly from here. Let's see. And look at the actual pod that was in charge of this request. So it looks like this came from the AI agents 7.9 whatever pod. We can go ahead and open this in Kubernetes Explorer. And so we can actually pivot from the LLM Explorer over to the actual infrastructure that is serving your AI application. And we can see here things like, how much CPU was used, how much memory did that pod use. So we can see that that large embedding batch doesn't actually seem to have taxed our resources at all, which is great. So on this page, you can see, things like the Kubernetes events, different logs, metrics like the CPU, memory usage, and pod counts. All of the other traces that pod was in charge of, as well as being able to pivot to even more things like opening up the actual cluster, like the high-level Kubernetes cluster that is serving that pod. So Observe makes it pretty easy to jump around between all of these different objects and kind of deeply explore the problem that you're trying to debug. So that was the first use case that I wanted to go over. I have a second scenario as well. Of course, there are like a wide variety of applications that we use these new language models for. One of them is embedding, but a more common use case is actually asking it for chat completions. So there was a case where the AI investigator got a question wrong, and when a user asked for memory usage metrics for a specific pod in the Capital One cluster for the last hour, we gave them the wrong cluster. And so we can use the LLM Explorer in order to debug, like, why did it give it the wrong cluster? Did it have the wrong context? Did it have the wrong prompt? Was the LLM just not feeling great that day? let's go ahead and start looking for that error trace. And so this particular case happened on May 8th. So I'll filter down to that time range first. And I'll filter down to workflows only, since I want to see the entire agentic workflow. And then I'll search for the actual question that was asked. So we can just search in the content field here. For the workflow that answered the question, show the memory usage metrics for the monitoring V2 pod in the Camp1 cluster for the last hour. And there's one hit here. Let's go ahead and look more deeply into this one. And here, there's a bit more of a complicated trace here. If you recall from my overview of the AI investigator, it's actually an agentic application that goes between different control nodes and has different steps that it goes through in order to answer your question. And so we can see the overview of it going to this phase of initial planning, and then the orchestration agent deciding what tool to call next. That's this planner.task span here. And then it chose to call the observe agent. So then we can see the chat log associated with that. And then control went back to that orchestration agent, the planner here. And so we can see the entire flow of this agentic workflow and all of the steps that it took to answer your question. And for each of these different nodes and for the workflow as a whole, you can see like the input that was associated with it. Let me just put that up. Looks like the input for that one got minimized, but we can see the input and the output associated with it. For example, for this one, it wanted to output like the investigation notebook as well as the job status and all of the different like this chat history. Now drilling deeper into the actual calls to the LLM, we can see like the prompts that was passed in, including like the nicely rendered into Markdown, including this, and it's marked as the system prompts versus like the different user prompts that we asked it to complete. We can see the output. It seems like that one got minimized. Let me try reopening it. Yeah, the completion. Let me minimize that one there. Yeah, it seems like the UI still has a couple bugs in it, but after a couple iterations, we can see that the LLM output this tool call that filled in that it wants to use the observe tool, the observe sub-agent, giving this status update, this instruction, and this section title to display to the actual user. Now to figure out why did the LLM actually give the wrong answer to the user, we need to look more closely into the observe agent. So the issue here is that the underlying issue is that we actually have two clusters associated with Capital One. We have kubernetes.cap1.observing.com and kubernetes.cap1uswest.observing.com. And so we can see that the LLM chose to use kubernetes.cap1.uswest.observing.com. But from the query that we asked, we would have expected it to only use the other one. So we can see that it made this tool call for Kubernetes container memory, and it filled it in with these parameters. Now, in order to debug why it chose the wrong cluster for Cap1, we can look into the actual prompts that were passed in. Now, in order to give the observe agent the important information that it needs, we pass it this section of context in which we provide it all of the pieces inside of our knowledge graph, inside of our vector database, that are relevant to the query that was asked. So we do a semantic similarity search over all the entities in our that we know about in your system. And so in this section of the prompts in which we put in that context, we can look for where the cluster name is. So it did retrieve Kubernetes.cap1 US West, and it did also retrieve Kubernetes.cap1.observing.com. Within our prompts, and we could verify this by looking at the system prompt, we actually have a section that says you should weight kind of earlier ones more heavily than the later ones, because this is ordered by semantic similarity. So the issue here was that for our retrieval step, we thought that Kubernetes.cap1 US West was more semantically similar to the user's query than Kubernetes.cap1. And so it ended up showing up earlier inside the context, which is why the LLM made that mistake. And so by using the LLM Explorer, we were able to find the specific trace that was associated with the erroneous query, drill further into it, explore kind of all of the steps that were taken inside this agentic workflow, and drill further down into the individual like chat completion calls and see exactly what the input and output was that we passed to the LLM. And we can also look at, again, we can look at the duration of the spans. We can also see like which calls took the longest inside the entire agentic workflow through these charts up here. We can see how many tokens were used, what model that you asked for, as well as how many cache tokens were used, how many tokens did it output, how much did we actually put into the context, and all of that information. Right, I think that's pretty much it for the demo that I wanted to show you guys. Back to you, Kevin.
Awesome. Thank you, Austin, for walking us through the great new functionality in LLM observability. And with that, for those of our viewers who are existing Observe users, if this is interesting, this is something you want to try, I'd encourage you to reach out to your support team and they can help you get set up on it. If you're new to Observe, you can, of course, start a free trial and try this for yourself, but I would encourage you to use the contact us form, and then we can also get started that way and help you get started on LLM observability for your apps. And with that, Grant, I think we have some time to take questions.
Yeah, thank you, Kevin, and thank you, Austin. We have a few questions that have come in. I'll ask them in the order that they were entered. And the first question is, how do you define LLM observability versus traditional observability? And what are the minimum signals teams need on day one?
Yeah, so LLM observability has very different features from regular observability in that there's just different things that you care about. With regular observability, you care about like, is your application like, did it return it like a 500 error code? Did it like, is the service down? Is it taking too long? And some of those things, and of course, these things you also care about for AI applications. But with AI applications, you also really care about kind of more qualitative errors, like the LLM getting something wrong, instead of it straight up giving like an error. And you also want to track things like token usage, in order to track your costs, as well as kind of different metrics about the actual quality of the responses that you're providing to the user. So it's kind of a different, there are additional things that you really care about in addition to the regular observability use cases. As for what you need on day one, I guess it depends a little bit on how you define day one. But if you've literally just started creating your AI application, if you're pre-users, you basically just want to understand like, hey, does what I built work? Like, is it giving the answers that I need? Am I providing the correct context to the LLM? And in those cases, you need to start with, you just need a way to understand like, hey, what did I pass into the LLM? What did it get out to me? And from there, you can debug like what you're actually putting into the prompt and iterate from there. Now, once you start getting users, it becomes more and more important to track things like what is the actual cost associated with all the LM calls that you're using. Are there places where you can optimize? In those cases, our offerings for accounting the number of tokens that you're using, and splitting by model provider, and things like that are very useful in order to ensure that you aren't putting all of your funding into OpenAI.
Cool. Next question that just came in. How do you distinguish embedding token usage from generation usage and tie it back to specific indexing jobs?
Yeah. So um, OpenLLMetry, which is what we use in order to instrument our application, will actually like look at the calls that you're making with, say, the OpenAI or Anthropic or whatever SDK, and distinguish and mark the trace with whether or not it was like um, an embedding call or a completion call. And from there, we can then visualize it in the LLM Explorer. We're able to filter down specifically by, for example, those chat completions versus the embedding completions. And so you can distinguish between them on the LLM Explorer that way.
Excellent. The next question that just came in, what do I need to do to set all this up?
Yeah. So in order to set all this up, you basically just need to first you need to instrument your code. This is as simple as just following the documentation for OpenLLMetry. They have integrations with most of the popular model providers, as well as the languages that you're most likely using, Python or TypeScript, and as well as some others. So once you have things instrumented, you can then go to the observe documentation in order to install the observe agent. And that's it. That's all you need to do. Once you have the observe agent and your code instrumented, it'll automatically send your data over to observe, and you should see it populate inside the LLM Explorer, as well as being able to observe your Kubernetes infrastructure and service infrastructure as well.
Awesome. Give it just a few more seconds here. I think that's, well, 1 second. Yeah, that's all the questions that we have. Jay will reach out to you after the webinar. Thank you for posting your note. I want to encourage everybody to take a look at the LLM Observability blog. There's a link posted in the chat. We also have a free trial that people can get started with. The recording of the webinar today will be sent out this afternoon. I also want to make everyone aware that we've got a really exciting webinar, the next upcoming one, which will be Masterclass in Observability at Scale. Lessons learned from Stripe, Google, and petabyte scale enterprise deployments. On this webinar, we'll have our CEO, Jeremy Burton, our President of Engineering, Chi Jin, and also one of our founders and Chief Product Officer, Jacob Leverage. So it should be an exciting session. We'll send an invite to everybody who's on this webinar. Appreciate everyone for joining us today. Thank you so much. And this concludes our session.